Hello everyone and welcome to the Get Me class. I'm Vivekanand Talgadi, your chemistry instructor. In this particular session, we will be taking a look into the different types of the defects that are found in the crystal lattice. Now, whenever we take a look at a particular solid crystal, condition is that at 0 degrees, okay, or we can say as an absolute 0 degrees, at the absolute 0, what happens is all the particular lattices or the spheres, we can say that in this particular way, that all of these particular arrangement are perfectly ordered in a crystal. So here, the crystal tends to have a completely ordered lattice. So here, the lattice has a perfectly ordered arrangement of the atoms or the ions, or you can consider them as a sphere, right? So here, this occurs when the temperature is 0 degree. So all these particular things have a completely ordered arrangement. Okay, so here the main point is the arrangement of atoms or the ions are in a perfect order, right? Now, as the temperature increases, that is, I would say as at higher temperatures, they show certain deviation from this perfectly ordered system, right? So therefore, at the higher temperature, the crystals show deviations from their perfectly ordered arrangement. Now, in this particular case, this deviation, as what we see, this deviation is called as the defect. Okay, so therefore, any deviations from the perfectly ordered arrangement, we call it as, either you have the two terms, either we call it as an imperfection or we call it as the defect. Okay, so is called as defect or imperfection. Now, all the particular lattices, what we see, they undergo some or the other type of defects. There are a lot of types of defects which we need to understand. So in this particular video session, we will be talking about the different types of the defects that are possible in a given crystal, whether the crystal is ionic or whether the crystal is non-ionic. It is going to exhibit some or the other type of defects, right? So therefore, our entire defects, we can classify them into the first part as what we can call it as. The first term, we use it as the intrinsic defects. Okay, now usually the intrinsic defects are the defects which are found in a pure solids. Okay, so therefore, the defects observed in pure solids. These particular defects, we call them as the intrinsic defects. The second one is called as an extrinsic defect. Okay, so extrinsic defect, these are the defects which are observed again because of the presence of the impurities in the substances. Okay, so these defects arises whenever there are impurities in the solid, right? So therefore, the defects that arise due to the presence of impurities in solid. Sorry. Okay, so now the main part of the entire defect actually starts from this point. That is, we have a particular defect which is called as the point defect. Now, this is the most important one. Let's try and understand with the help of an entire crystal lattice. Okay, now let's consider this is the entire lattice. And let's say that in this particular lattice, we are going to have n number of spheres which are correctly arranged, something like this. Okay, now in this entire series of arrangement, let's say that in this case, one out of these particular lattice points or the atoms or the ions, or in this case, the sphere. Here, the defect is caused because of the departure of an atom or an ion from a completely ordered arrangement. Now here, let's say that this is a completely ordered arrangement, right? So if this is a completely ordered arrangement here, let's say that in this case, one out of them goes missing. Let's say this particular point goes missing here. So at this particular junction, as here, this is a point which went missing. Now, here the defect is caused because of the missing of an atom or an ion from the completely ordered arrangement. This particular situation, we call it as a point defect. So therefore, a point defect is a defect. The defect caused due to the departure, or what we can call it as an absence, okay, due to departure of an atom or ion from the completely ordered arrangement. Right? From the completely ordered arrangement. Now, this gives rise to the point defect. Now, we are going to speak in detail about this particular point defect, of course. The second type, as what we have, is called as an extended defect. Now, this particular defect is also called as lattice defect. It has the other term as what we call it as the lattice defect. Okay, so in the lattice defect, what happens here is that if we have the entire perfectly ordered arrangement, let's say this is going to have a perfectly ordered arrangement of all the particles over here. Now here, the defect is not just at one point. Here the defect is either for the entire line or the entire plane. That means here the entire line goes missing. It can be this entire line goes missing. This line consists of the entire array of atoms or the ions or the spheres. So if this entire system goes missing, or the entire plane can go missing. All right. So here, what is happening is that the defect is extended over the microscopic region. That means here the defect, whatever we are looking at, it is not just restricted to a simple lattice point. Rather, the defect is extended all over a bigger area. The area can be just a line of atoms, ions, or spheres, or that particular line can be the entire plane or the surface. Okay, so here it extends over the microscopic region, right? So therefore, the deviations from a completely ordered arrangement in which extends, that particular defect extends over the microscopic region, we call it as a lattice defect or an extended defect. Okay, now this particular extended defect is of two types. As I said, that it can cover the entire line. Okay, if the particular defect, let's say, if the defect, okay, extends over the line, okay, so that time we consider it as a line defect. Okay, on the other hand, if we consider that if the defect extends over the entire plane, or we can say as a surface, right? So at that particular moment, we call it as the plane defect. So here, that is, in this entire scenario, there is going to be a particular defect that has been observed, correct? So here we observe irregularities in arrangements. So therefore, the irregularities in arrangement, that is the defect when it is going to extend over the line, we call it as a line defect. If this particular defect extends over a plane, then we call it as a plane defect, right? So now, moving further with the next type of defect, and which we call it as a stoichiometric defect. So in a stoichiometric defect, okay, that is a point defect. The point defect, what we were looking at, this particular point defect is further classified into stoichiometric defect, okay. Now, we need to observe what exactly is this particular stoichiometric defect. Now, whenever there is a defect and that defect occurs in a particular solid in such a way that it does not disturb the stoichiometry of that particular compound, then we regard that particular defect as a stoichiometric defect. Okay, let's try and understand that with the help of other classifications also. So first, let's write it down over here. The defects which do not affect or disturb the stoichiometry of solid, they are called as Yes, we have the stoichiometric defect. Right? Again, these stoichiometric defects are actually classified into two parts. Okay, now the first type of the stoichiometric defect is called as the vacancy defect. The vacancy defect. The second type of this is called as the intrinsic defect. Right? So now let's first take a look till this particular point and then we will proceed further. So type of crystal defects. First one, as what we have already seen, the intrinsic defect, as these particular things are seen in the pure crystals. Extrinsic defect, these are the defects which arises because of the presence of the impurities in the solid. Point defect, these are the defects which are observed when an atom, ion, or any particular particle is missing from an orderly arranged crystal lattice, right? So therefore, these occur at the lattice point or the sites in the crystal. Extended defects. Now, we have already seen extended defects. These are the defects where it's also called as the lattice defect, wherein the atoms, ions, are missing throughout the entire line or the entire plane. So here, what is happening is this particular defects are extending over the microscopic region. So these are the present in one or more dimension, either the line, if we are considering line one dimension, if you are considering the entire plane, then it becomes as a two-dimensional defect also, right? So stoichiometric defects. So these are the defects which are also called as the intrinsic defects or the thermodynamic defects. Correct. So these are called as the intrinsic defects or the thermodynamic defects. They are of two types. One is called as the vacancy defect and the another one is called as the interstitial defects, as what we have already seen. Now, we will observe the entire vacancy defect and the interstitial defect into a complete section. Now here, when we are speaking about the vacancy defect, so when we are speaking about the vacancy defect, now these are the defects which are caused in the crystal lattice when a particular vacancy is created by removal of certain points. Okay, so therefore these are the defects when some of the lattice points, in the crystal are vacant. That means they are missing here. So that particular point, that particular atom or that particular ion is actually missing from that particular point, right? Now, the crystal is said to have an vacancy defect. Now, if that particular thing is missing, that means it is going to affect the density. Okay, so therefore, this particular defect affects the vacancy. Sorry, it affects the density. It affects the density of the given solid or of the given substance, right? So this is about the vacancy defect. Now, second one, as what we have is the interstitial defect. So second one, the interstitial defect. Now, the interstitial defect, in order to understand that, we need to first understand what exactly is an intersite. Now, let's consider the entire lattice point. Let's say this is a given lattice. Okay, in this given lattice, what we have is, let's say that these are the given spheres. Something like these. Okay, now let's say these are the given spheres over here. Right? Now, the second line of spheres are these. Now, if I'm going to continue like this, then of course, I am going to get this kind of portion repeating again and again. Now here, if we observe this part, only this part, okay, let's take only this part for our study. Okay, now let's remove this over here. Now here, when we observe in this particular scenario, if we observe this particular region, this is a region where we see that this particular region here or this particular region over here. These regions are the empty spaces, and these are going to be distributed throughout the entire lattice. Okay, now these empty spaces, we call them as the voids. Sometimes they are also referred as the intersites. Right? Now, these intersites or the voids are distributed throughout the entire lattice. Now here, what happens is sometimes these particular voids or the intersites are going to be occupied by smaller atoms. So here, usually what happens is these smaller atoms will come and occupy these particular regions. So when a smaller particle or the smaller atoms or ions will occupy the empty spaces, then we call this particular defect as the interstitial defect, right? So this is about the interstitial defect. Therefore, what is going to be as this particular defect? Now, there are certain important key points that we need to remember about the interstitial defect. These are the defects which are usually observed in a non-ionic solid. So therefore, non-ionic solids exhibit the interstitial defect. First point. Now, because of the impurities coming and occupying the intersites, usually what happens is affects the density. In this case, the density of that particular substance is going to increase. So here, the density of substance increases, right? So this is about the vacancy defect and the interstitial defect. Let's observe all these points. So stoichiometric defects, these are the defects which do not disturb the stoichiometry of the compounds. These are classified into 2 points. That is a vacancy defect. These are found when some points, that is the lattice points in the crystals, are missing or vacant. Then the crystal is said to have the vacancy defect. These defects are going to decrease the density. Interstitial defects, these are the defects, okay, wherein the empty spaces, we need to understand what exactly is the intersite or the void. So here, the voids are distributed throughout the entire lattice, and these particular voids, we call them as intersites. And sometimes the smaller atoms occupy these voids. So therefore, these are exhibited by the non-ionic solids, and here we observe there is an increase in density of a substance, right? So let's go with the next point. So in the next point that we need to observe is one of the most important defect, and that what we call it as the Scotchy defect. These particular defects are shown by the ionic solids. Okay, so when we observe about this Scotchy defect, now these are the defects which are exhibited by the ionic compounds. Now, in this condition, ionic compounds here, when we are speaking about the ionic compounds, it is going to have two different types of ions, and those are the cations and anions, right? Now, the first condition in the Schottky defect is that these ions should have the similar, it should have the similar sizes. That is, the size of the cation and the size of the anion have to be the same, right? Now, in the second case, with respect to this, is that here in this particular thing, a vacancy is created. A vacancy is created in such a way that the cations are missing. These undergo missing first. Okay, now in the nearby vicinity, that means in the nearby region of this particular cation, the equal number of anions go missing. Okay, so therefore we can say that equal number of cations and anions are undergoing missing. So therefore it is going to have a neutrality. So a neutral state is achieved, right? So therefore the neutral state is achieved. Now we need to understand that when the neutral state is achieved, yet we are going to lose some amount of cations, some amount of anions in this case. So therefore here the density is affected. So density decreases a lot. So here the density decreases. The next important point as what we need to observe is that with respect to the coordination number. Here, the coordination number in these particular compounds, the coordination number in these particular compounds is quite very high. Okay, so therefore these are the key points for our Schottky defect. So first point is these are usually shown by the ionic compounds. Now ionic compounds, that means it is going to have the cations and anions. So in this particular defect, what is going to happen is the equal number of cations and anions are going to be missing, due to which the electrical neutrality is of course created, but with a decrease in the density, right? This is exhibited by those particular compounds which have a higher coordination number, right? So let's observe all these points first. So in this defect, it arises due to the vacancy at the cationic sites, and then the equal number of vacancies at the anionic sites. In ionic crystal, electrical neutrality is maintained. This type of the defect occurs in the coordination or the ionic compounds with a high coordination number, where the positive and the negative ions, okay, where the ratio of cations and anionic radius ratio is approximately equal to 1. Now, example that what we have is over here is the NaCl, that is the sodium chloride, cesium chloride usually give the same, right? So Schottky defect is found in the highly ionic compounds. Large number of vacancies in the lattices are formed, due to which it lowers the density, right? So let's observe the next defect. So in the next defect, as what we have is called as a Frankel defect. Okay, so the Frankel defect will be our next point of discussion. So Frankel defect. Now, here, when we are speaking about the Frankel defect, this particular defect is exhibited. It is exhibited again by the ionic compounds. Now, here what happens is the smaller ions are affected. Now, what exactly is a smaller ion? The size of cations is small when we compare to that of the size of the anions. So therefore, in this entire scenario, what exactly happens is the cations are missing from their lattice points. Now, as it is missing from their lattice point, what it does is it misses from its lattice point and it goes into the intersites. So therefore, these occupy, that is the cations occupy the intersites. Okay, so therefore I can say that this is a combination of the two different defects. It is a combination as the cations are missing from that point. Okay, so I can say as this is nothing more than a hybrid defect, which is a combination of two things. The first is it is a combination of a Scotchy defect, right? It is a combination of Scotchy defect as the cations are missing from its lattice point. Secondly, it is going to occupy the intersite, so therefore it is exhibiting an interstitial defect. It is exhibiting the interstitial defect, so therefore it is a hybrid combination of these two defects. Now, Frankel defect is a defect wherein we observe that a large difference in the sizes of cations and anions are observed, right? Secondly, when we observe about the coordination number, here the coordination number of these particular substances are usually low. So low coordination number is observed. Low coordination number. Usually it is coordination number 4 or coordination number 6. Now, as the cations are missing and it is going directly into the intersites, the cation is not coming out of the entire lattice. Thus, the density is not affected. So in this entire scenario, we can say that here in this case, the density remains the same, right? So let's observe all these points one by one. So here, a Frankel defect. This type of defect arises at the vacancy at the cationic site. That means cation is going to go missing. The cation moves to the another position that is between the two layers. That is, it is going to the intersite and it is surrounded by the greater number of anions. Frankel defect is usually observed or favored by the larger differences in the size of the cations and anions. Now, compounds having the ions of different sizes, that is, the radius of cation divided by radius of anion is low, okay, for a cation. So therefore, the cation displaces from its point. Now, in this particular compounds, the coordination number is low, that is 4 or 6. Example, zinc sulfide, silver bromide, silver iodide, and silver chloride. The Frankel defects do not decrease the density of the solid, right? So thank you for watching. Do take care.